class on interpreting and communicating statistical results. Um, I teach a lot of classes. Like some of you, my main job is as a teacher, professor, and I want to say that this may be my favorite. I really like this. I think I feel useful because I feel like there are some skills here that can be applied in people's work, and I'm really excited and happy to share this with you. So the goal is, as the title says, twofold. I want to give you a framework and some tools to be able to interpret your statistical results. I feel pretty strongly that there's a big gap in our teaching and in our statistical training. Oftentimes, we spend a lot of time talking about how to fit models, what kind of models we need for certain data. And then in the end, it just feels like we're kind of stuck with this complicated model and we don't quite know what to do with it. And so I want to give you first a conceptual framework for how to think about interpreting statistical results, and then some very concrete tools for you to communicate those results, because in the end, that's what matters, right? You don't want to estimate statistical models and then just keep them to yourselves. You want to communicate them. You want to have impact. And so I want to give you some very concrete steps that you can follow, and tools that you can apply to communicate better and to interpret in ways that are transparent, that are robust, and that are very clear and meaningful for your stakeholders, for your readers, for your colleagues, and for yourself. So the first thing I should say is thank you. I feel very honored that you'd commit to spending so much time with me. It is really great. It feels good, and I'm glad you're here. So I'm really. It is a privilege for me, and I'm really going to do as much effort as I can to make it worth your while. So thank you. So who am I? I guess you've heard the bio from Steve, but I'm Québécois. So I'm a francophone from Canada. I live in Montreal. I studied economics and political science, and I am now a professor at the University of Michigan. No, I'm a PhD at the University of Michigan. I was there, and I'm now a professor in Montreal, which is my hometown, and I'm delighted to be here. I teach at my alma mater, so this is pretty cool. I like it. So this is my kind of life journey. And what's probably most relevant to you in the context of this class is that beyond my teaching and my research in the niche field that I do work in, I'm really into writing code. And in the last few years, I've thought a lot about how to create workflows and how to give tools to people so that they can do their work more efficiently, and so that they can generate results that are clearer. So I've been publishing R packages for a while. So the first one was while I was in grad school. That's a long time ago now. But now more recently, I've spent the last few years really focusing on these two packages, on marginal effects, modelsummary, and tinytable. And they'll be the core part of what I'll be teaching in this class. We're really going to focus on that. And so I've really basically dedicated the last 4 years of my life putting this together, because I believe in that mission, which is making the interpretation of statistical results more accessible, clearer, and eventually more correct as well, because there's a lot of confusion about terms. There's a lot of confusion about terminology, and also the tools are not always that great. So I've been working a lot on tooling and on concepts to make this easier for people. Very recently, I was named as an associate editor of the R Journal, which is it's the official peer-reviewed journal of the R Foundation, which publishes the software. So that's been fun, seeing it from the more macro view of what's going on in the open source community has been tremendous, because there's a lot of people doing really good work, producing tools for others. So that's been a fun experience. All right, so here's the course structure. At first, we're going to see a conceptual framework because, of course, that's essential. If you want to interpret statistical results, you need to know how to approach it. And it's going to be a very structured framework. So I'm going to give you 5 questions that you need to answer for every quantity of interest. And with those 5 questions, you'll be able to interpret almost any statistical model in a way that makes sense and that is hopefully intuitive for your readers. Then after that, I'm going to talk about hypothesis tests. Hypothesis tests, you've seen those in statistics, right? The null hypothesis test. And we're also going to talk about equivalence tests, which some of you might not have seen, but which are super useful. And I'm going to present hypothesis tests at first because it's kind of a building block for what we're going to see later. Because we're going to be able to conduct hypothesis tests on all the other quantities that follow. So the 3 main quantities that we're going to inspect are predictions. Those are the predictions of our models. That's sometimes called fitted values, right? Then comparisons. Those are going to be comparisons between predictions. So they're going to be functions of 2 predictions. So oftentimes it's going to be like a difference between 2 predictions. So for example, the survival rate for older people versus younger people from a certain sickness. And we're going to compare these 2 quantities. And then slopes, which are sometimes called marginal effects in some disciplines. This is going to be a measure of the strength of association between two variables. And then at the end, for the last day, probably, we're going to talk about how to communicate these results. So the first one is what happens after you fit a model? How do you convert the model fitted results, your coefficients, basically? How do you convert those into reasonable, interpretable insights? And then at the end, it's going to be how do you easily build those tables, those plots to be able to communicate your results. So this is kind of the content structure. And then on the other side, we see the format. So the format is going to be me giving you some information in a very standard lecture style. Then for every block, so for hypotheses, for predictions, for comparisons, and for the last one, there's going to be a practicum. So there's it's practicing. You'll run some code and you'll have to, it's pretty easy. So don't worry too much about this, but I just want you to be able to run this stuff in your computer to make sure that you've at least done it a few times. After that, after you've put the information into practice, I'm going to push things a bit further by going into some more detailed case studies. So for example, I give you the lecture on predictions. I have you run some predictions with the software on your computer, and then I go into a more complicated case studies for predictions on non-representative survey data or something like that. Okay, so it'll be a more specific set of information. And then, of course, after every section, there's going to be an open Q&A. You can ask questions about the specific topic or about your research as well. If you have some concerns or if you have some questions about how to apply the stuff to your work. I'm going to build in a few 10-minute breaks, maybe at the end of every hour or something like that. Chance to rest your eyes a little bit. There's lots of resources available. So this is the Dropbox. I'm also going to put the link in the chat. So if you click there, you're going to be able to download all the resources for this class. There's 2 articles from the Journal of Statistical Software on some of the main software that we're going to use in this class. Then I've put all of the slides for all 4 days. I might do some slight modification over the course of the class as I notice things and as I look at them at night, but the basic slides are all there. What's maybe nice is that they're in Quarto format, which is a format. Have you ever heard of Quarto? Is this something that you're familiar with? Okay, I see some no's. All right, so Quarto is a notebook format. So it is a way in RStudio, you can write a document that uses something called Markdown. Markdown is a syntax that's very simple to describe what's a header, what's a bullet point list, and it's just plain text. And then with Quarto, what's nice is that you can write your text and you can embed code in your text. And then the code gets executed and gets presented as a nice HTML document or as a PDF document, or in this case, as a set of slides. So I did all of my slides with this syntax, with Quarto, and with embedded code in the slides. And so you can see exactly how I did it because the raw documents are all there. So if you're just curious about how I did one thing, you can always just look at the raw code. The slides are in HTML, so you can open those. And then one resource that is kind of neat, I think, is that I've also separated all the code that I display in the slides into separate R scripts. So you can go into RStudio and open the scripts that correspond to a set of slides. And you can, if you want, just run all the code alongside the slides. So when I explain the topic, maybe you just want to run that code just to see if it works on your computer, what happens if you modify something. So it's all there. Also, there's on Dropbox, there's a folder called Breakout. In the Breakout folder, you'll see some HTML documents that you can open in your browser, and those will be our hands-on exercises. So after every blog, there's going to be a hands-on exercise, and all the code is in there. You can copy it in your RStudio, and you'll see most of them are pretty simple and have it's almost fill in the blanks kind of exercise. Right? I give you a command, and then I say replace me, and you'll replace the chunk of code with something that's relevant to the question. The breakout, the practicum exercises will be maybe 20 minutes after each block. That's maybe how long it's going to take. And then there's also data for all of the examples that I give during the class. It's all there, so the raw data sets are. Does everyone have access to this? Can you see the Dropbox? You're good?
Yes.
Good. Great. If you don't see it, then okay. So I say the data is on Dropbox. What are these data sets? Well, some of them come from the R datasets webpage. So this is maybe useful to some of you, so I'll just mention it. It's a collection that I put together. Basically, what I did is I installed a lot of R packages, and some R packages come with built-in data sets that you can use. So they just ship the data sets that they use for examples in their documentation. And what I did is I scraped all these data sets and put them on a website. So if you click on this thing, our data sets, I can put it in the chat room. If you click there, you'll see that there's a collection of 2,300, I think, free and documented data sets. So if you need to illustrate something to someone, teach, that's really good for teaching. If you need to try some software, there's a ton of data sets there that you can use. So the data that I'm going to use comes from our data set. The first one is the Contoso cameras data set. So this is more marketing maybe, but it's a simulated data set on the quantity of cameras sold. This is going to be for the hands-on exercises, so you'll play with this one. And it comes from Microsoft Business Intelligence. It is in Dropbox, so you can load it in your R with these commands. So just to give you a sense here, the read RDS, it is a command that is in the basic R, right? Everyone has this command as soon as you install R, and it is a command that is meant to load into memory some binary data sets. So you've probably seen CSV files in the past. If you use Stata, they save their files as .dta usually, and SPSS has some extension as well. Is it .SPSS? Maybe SPS, I think. Well, in R, how it works is there's also a binary format that is .rds. So you can read the data in memory and then use the head command, which shows the 6 first rows of this data set. So notice that I've used the little dots here, and this path is of course going to depend on where your working directory is set in R. So if you're working in the breakout directory, for example, maybe you can remove the 2 dots in order to load the data set. So just keep that in mind. We'll come back to this when we do the hands-on exercises. I'll make sure that everyone has the data loaded, but you can already try that if you want. The second data set that we're going to use, and this one is going to be used mainly for the slides, is from a randomized control trial from this Thornton article from 2008. And so what the left graph shows is perhaps unsurprising, but still very depressing, that there's a ton of deaths every year from AIDS, HIV/AIDS. So this is a graph for the African region until 2019. So that's hundreds of thousands of people, right? That's really terrible. So what Thornton did is in the study is they wanted to make sure that HIV testing was effective as a strategy to prevent the spread. And many international organizations and governments have done this, right? They've put investment to do counseling and testing. But one problem that's been observed is that you can do counseling, you can do testing, you can even do home tests, like you can go door to door and do the tests at people's places. But sometimes the people get the test, but don't get the result. They don't go to the clinic to fetch their results, right? So in that case, the intervention has failed essentially because you've tried to give them information, but if they don't go get their results, they cannot act on the information because they don't know, right? So what the study has done is really simple A/B tests, right? Like you have two arms. The study is actually a bit more complicated than that, but we can do simple. So people in rural Malawi were offered a free HIV test at home. So people were going door to door, really literally, to give it for free. The problem is that people do not pick up their test results at the clinic or at the test center. So what we do, what they have done in this context is they've set up a random treatment where they would give vouchers to people, $1 to $3, because they also wanted to see how much money you had to give to people to incentivize people properly. But we're only going to look at whether someone gets an incentive in this class. So they gave vouchers. When a person picks up the result, they get this $1, $2, or $3. So remember, this is in rural Malawi, so it's not life-changing money, but it's also not nothing in 2008, right? So what they've observed is that when you get the voucher, you're about twice as likely to go get your result. I wrote seeing a result, but it really requires an action. Like people had to go to the clinic to pick up the result. So this is a pretty big effect, right? We don't give a lot of money, and yet it really makes a difference in people's behavior. They go learn their results. And as a second step, which we won't study in this course, but just for your information, they've also established in the Thornton study that when you learn that you're HIV positive, it increases demand for condoms. So that was considered a success for this intervention. It increases information, and then it changes behavior. That's the basic study design. Again, interrupt me if anything's unclear about this. It's pretty standard design, so. Okay. So in Dropbox, you'll find the HIV dataset, hiv.rds. You can load some libraries, right? Whenever we want extra commands in R from an extension library, we use the command library and the name of the library we want to load. So these two are going to be the mainstays for this class, marginal effects and model summary. Now I'm loading the data set using the command that I talked about earlier, read RDS. And then I'm going to use this command here. It's called the data summary _skim. And there's going to be a whole section of the class on this, but this is a nice showcase here. What this does is automatically it'll create a summary statistic table like this. So you have on the vertical axis, you have every variable in the HIV data set. So result is a binary variable, which is equal to 1 when the person goes to the clinic to pick up the result, and 0 if they don't. So what we see here is that the mean of this binary variable is 0.7. That's the histogram of the distribution. But what this says is that basically 70% of people went and got the result. Okay, that's the dependent variable. That's going to be our outcome for most of the models that we estimate. Now, incentive is the randomized treatment. So do you get an incentive to go? Do you get a voucher if you pick up your result or not? Are you in the control group? So if you're in the control group, remember, you don't get a voucher, you don't get anything. So 80% of people got the voucher. 80% of the people were randomized to the treatment condition. Now, amount is another variable that says how much was the voucher. So you have the mean. Village is just a village identifier. So they did the study in 119 different villages, and there's a indicator for which village the individual lives in, the age of the person, and then there's a variable called distance, which is a categorical variable with 3 categories: short, medium, and long. And that is how far you live from the test center. So one of the intuitions that we're going to have is incentive. If you get the incentive, it should increase your likelihood of getting the result, right? You're paid money to go get the result, you're going to be more likely to do it. And then distance, if you live very far from the test center, that's probably going to decrease your likelihood of getting the result. So that's it's kind of the basic intuition for this. Any questions so far? When I was in grad school, they prepared us to be amazing teachers by giving us a 2-hour class on how to teach. And that was not enough. But one of the tricks that I remember they gave us is that when you ask if people have questions, I have to count up until 12 in my head. So I do like 1001, 1002, and it takes a long time and it's awkward. But you might see me sometimes muttering because I'm okay. No questions. All right. So, oh, Sarah, yeah. No.
So I'm following along, and for whatever reason, when I run this code, everything under age, like so distance, short, medium, long, is not, I don't, it doesn't, like if I open up the object, I have information about that in the object, but in terms of what is returned, kind of that looks fancy in the viewer doesn't have that. So what am I doing wrong?
So you get all these variables, but not the ones below.
Right.
Okay, so you're probably using an older version of model summary because this is the categorical data display is a new thing. So try to update the package. If you do update packages models, I'm putting the command in the chat. If you write this and then restart your R session for the new package to work, I'm hoping it'll fix the problem. All right. Okay, so the idea is that our outcome is this result variable. Do people go get their result? The main variable of interest is this. That's our randomized treatment, incentive. Do people get the incentive? And then we're going to control for age and distance as well. So outcome, treatment, control variables. I use the GLM command. The GLM command in R is generalized linear model, right? That's a way of fitting statistical models that is from base R. That's one of the most fundamental commands in R. And then I set the family argument. And when I set the family argument to binomial, this means that we're going to estimate logit regression. Okay, so you've heard about logistic regression probably. That's a model that's usually appropriate when the outcome is a binary variable. And so this is what we're going to estimate. And then I said that data equals that. And that's because when I loaded the thing in memory before, when I loaded the data set into memory, I called it that, right? I said the that object with the arrow is going to be equal to this data set. So now I'm fitting the model and I'm going to display the result of that logistic regression estimation with the summary command. The summary command is the one that we teach normally when we teach base R. Intro to R, we showed that kind of command, and then it gives you a whole bunch of things like this. So the estimate, the standard errors, the Z values, the P values here for every coefficient. One thing to notice here is that there's a coefficient for distance medium and a coefficient for distance long. This is because the distance variable is a categorical variable. So we're omitting one of the levels of the categorical variable. R does this automatically. That's the reference level. This is a standard procedure. It's all normal. Okay. So uh, first, I just want to show you that, well, this looks awful and this looks a bit prettier. So this is one of the commands that we'll see in the last lecture of the class. Model summary, instead of using just summary, which is the base R command, if you use model summary, you're going to get a nice regression table like this. If you don't get this, and when we take a break, I can try to troubleshoot your computer, see if there's an issue I can fix. Okay, so now I've introduced the data. I've shown you the main model that we're going to use for this first part of the class. And now I want to highlight 4 problems that I plan or hope to solve in this class. The first one is simply that stats is hard. In principle, it shouldn't be. It doesn't have to be, but it kind of is in practice. So what I think we should all acknowledge is that stakeholders do not care about our coefficients. They don't care about our parameters. The readers don't either. What we care about is how to interpret them, how to give actionable insights, how we can influence, inform decision making, how we can characterize an effect size, for example, in a way that's transparent, easy to understand, and interpret. And so my contention here is that model coefficients rarely help us do that, except in the very simple linear regression case. Model coefficients or parameters are very difficult to understand and interpret. So the question for this class is going to be, how can we deliver clear insights from these complex models? Just to emphasize that point, this is the regression model that I just showed you, right? Logistic regression is something that's taught oftentimes in the first or in the second series of stats classes. So it's pretty basic, and yet I would argue it's very difficult to interpret, actually. So what do these coefficients mean? Well, one coefficient is log odds ratio, right? But what does that mean, a log odds ratio? I'm not too sure. Probabilities themselves are very hard to interpret. There's a massive literature in psychology and in behavioral economics, among others, that shows that people are terrible at interpreting probabilities. When probabilities are very high, we usually tend to underestimate them or act as if they were much lower. When probabilities are very small, we tend to overestimate the probabilities. We're really biased in our assessment of probabilities, and we have a really hard time interpreting them. And that works for, I mean, that stands for lay people, but also experts. So probabilities are very difficult. But when you look at an expression like this, which is one of the coefficients in the logit model, I would argue that if probabilities are hard, this is basically impossible. Um, Odds are a fundamentally weird quantity. They're a ratio between one probability and one minus that probability. And here we're looking at a ratio of ratios and then the log of that, which we can maybe exponentiate. But this is, if you tell me you have a very strong intuition, very deeply grounded intuition about a log odds ratio, I will be very impressed. But honestly, I probably won't believe you. This is just very complicated. So what do we do in practice with these logit models? Well, sometimes we just look at the sign, right? So if you look at the sign here, incentive, that's our treatment variable, the sign is positive. So that kind of tells us that the treatment is positive, right? If you get the incentive, you're more likely to get your result at the clinic. So that seems good. But what does 2 mean here? It's not that clear. Then one other thing you can do is exponentiate the coefficient. That's a very standard approach to interpret logistic regression models. If you exponentiate it, you get a odds ratio. But my argument from before kind of stands. Odds ratios are super complicated in my view, and maybe should not be the quantity that you communicate. There's fun things like the divide by 4 rule, which is a bit more niche, but if you cut this coefficient in 4, it gives you an upper bound on the effect on the probability scale, which is kind of neat, but not especially relevant to the class here. Just mention it. But really, the killer here is that even if you have these tricks, even if you can exponentiate your coefficient or look at the sign, that only works for a very specific model, right? It only works for this logit model, and you don't have a general view of what happens in other models. So what if you estimate a multinomial logit model? Or what if you estimate ordered regression, like Kirsten earlier, right? Or what if you estimate a GAM with some splines or some random forest that's a machine learning model, right? What if you estimate something more complicated? Well, then you're stuck because you don't have the technology of just exponentiating your coefficient. We don't know what to do in those cases, or at least really model experts maybe know, but it's really difficult. So that's a big problem. The second problem that I want to solve is that, or at least make some headway on, is that the terminology for these for these mechanisms to interpret results is super inconsistent. So I've put a long list of words here: fitted values, adjusted predictions, conditional predictions, marginal predictions, average marginal effects. So there's a ton of different words or expressions that are used when interpreting models, and this terminology is super inconsistent across fields. So what we want is really a framework to be able to think about these quantities and describe them in ways that are both accurate and transparent in order to dispel ambiguity. So a lot of people take shortcuts by saying, I'm going to estimate a marginal effect, but really people don't agree on what a marginal effect is. So we need a way to describe these quantities that makes sense to everyone, that is clear, and that is precise. So just to give you, this is my favorite example. So the expression marginal effect, which I've used for the name of my package, and maybe that was a mistake because I hate the term, but marginal effect is a concept that in fields like economics and political science actually means the effect of a small change in X, that's your treatment, on Y, that's your outcome. So it's really marginal in the sense of infinitesimal, right? It's a tiny marginal change, and that's the idea of a marginal change in economics and political science. It is really the derivative. It is a slope, right? A derivative is the effect of a tiny change, and that's what economists mean when they talk about marginal effects. But everywhere else, so in the life sciences or in statistics proper, when you talk about marginal effect, it's actually the average effect across some subpopulation. So marginal here means marginalizing, right? So that's a process of taking the average across some dimension. And so in one case, we talk about the derivative. And the other case, averaging is basically a form of integration. It's an integral. And in mathematics, derivatives and integrals are, of course, complete opposite operations. And so the term marginal effect here can mean two really strictly, literally opposite things, which is completely crazy. And yet people keep using that term and get into long Twitter fights about the use of that term, which I have got myself caught in many times. I regret my time on the internet. Anyway, we have inconsistent terminology and we need a framework to think about it. The third problem is that, as some of you know, R can be super powerful. CRAN, which is the archive of packages, right? The way to download packages is fantastic. But sometimes documentation across packages can be hard to parse, even if it's detailed. And then the functions and the arguments often behave very differently in different packages. So if you estimate a logit model, or if you estimate an ordered regression model, for example, your model object that you're going to create is going to be very different. The way to extract coefficients or the way to make predictions from that model is going to be very different from one thing. So one effort that I'm going to make in the next few days is try to show you ways to make the process more uniform, regardless of the package that you're going to use. It's going to be the same steps to interpretation. And then the final problem that I hope to at least partially solve is that drawing tables and plots is super tedious. So I don't know if any of you have ever worked with LaTeX. This is an example of a LaTeX table that is really not that, it should not be very complicated, but this code is awful. And if you've ever tried to format tables in Word, you know that it can be challenging. And so I want to make this process a bit easier for you. All right. Any reactions or questions about this? 9, 11. All right. Solutions. So first, I want to present a conceptual framework, and it is going to be a general purpose technology. So how do we interpret the results of almost any type of model? Same steps every time. And then I'm going to try to help you be clearer and more precise when describing your quantities of interest. What is the effect that we're estimating? What group are we making predictions on? What kind of prediction? And really, I hope I'll be able to convince you that this conceptual framework is actually pretty easy. So it makes sense. We're going to see the steps. It builds on one another, and it should be good. So this is really a general purpose technology that's going to work for a lot of things. Then beyond the concept, I'm going to present some tools that are really Swiss Army knife like. So it's going to be a one-stop shop for all your model interpretation that supports 100+ model types. So almost any of the standard statistical models that you want to throw at it work, and even fancier ones if you want to do GAM or Bayesian models, or a lot of machine learning models are supported as well, using one simple and unified interface. So that's kind of a neat thing. It is reasonably fast, flexible, and then composable. I'll come back to this because that's one of the main features. All right. So just to give you a sense of what you can do with this. So with marginal effects, you're going to be able to interpret the results of simple GLM models like the logistic regression models, but all these complex models are supported. A bunch of stuff for causal inference. So if you ever heard of something like G computation, that's super easy to do. The categorical outcomes are supported, of course. Equivalence tests, interactions. So if you're interested in effect moderation, for example, so it does this treatment work better for men or women or something like that? Supported. Conjoint experiments, which is a type of survey experiments. Inverse probability weighting, machine learning, matching, multiple imputation, a bunch of things are supported. And all of this is documented on a website that I hope to transform into a book soon, with something like 30 chapters of free documentation with detailed case studies. So you can always go back to it. All right. So the libraries we're going to use are those. So marginal effects for interpreting the statistical results. That's going to take one model that's already been fitted, and it's going to give you quantities, or allow you to estimate quantities that are more meaningful, more intuitive. Then model summary is going to be to produce model and data summary, plots and tables. A tinytable that's going to be used to customize tables. So if you want to underline some coefficient or some quantity of interest. ggplot2, which is the standard, well, not the standard library, but the almost dominant library to draw plots in R nowadays. It's really great. And then Quarto to create documents and the slides that I'm presenting to you. Those are optional things, optional packages you don't need, but I'll use those in case studies. Okay, so this is the code that you can use to install the latest versions of the packages. I'm going to paste this in the chat, but there's also a file called install me in the Dropbox. So if you load that script and run it, you should be able to install all of the packages that we're going to use in class. After you install the latest versions of these packages, it's really important to restart your R session. So I'm just going to show you. So RStudio. Okay, so this is RStudio. If you go to the session menu here, you can do restart R, right? And this is going to keep your session open, but you see here that you've started a new session. And then when I execute library marginal effects, just to know, are the fonts big enough, or should I make it bigger? Yes. And
Oh, yes. So I'm wondering, so the organization that I work for is a little bit finicky about downloading softwares that they haven't fully reviewed for security. And so I'm wondering if I need to use my personal computer or this work computer for some of the things we're doing. And so my specific question is, does the Quarto package need to be installed um, separately from within our studio in order to function? It looked like there was a separate app installation as well.
I think that might be the case for Quarto.
Okay,
Yes.
okay,
However, Quarto is really only in the last day of the class,
okay,
and I only used it for now to create my own slides. So you
okay.
will not need it to run the thing. So if you can install the packages
Thank
within
you.
R, you're
Okay,
fine.
thank you.
So my question earlier was, is the font big enough, or should I? No. Okay. So let's do like this. Okay. So now I execute this, and then I run session info. And when I run session info with the capital I, right, I see all the packages that I've loaded in my session. So if I scroll up, it says I use R version 4.4.1, which is the latest R version. And then if I go down, I see that I've attached this package called marginal effects 0.21.0. That's the latest version of marginal effects. And if I do this here, model summary, and I execute this, and then I execute session info again, you'll see that now I have two packages loaded in memory, these two. And those are the latest versions of both. So if you install it with the install me, then you go to session here, restart R. Then in principle, you should be able to see that you have the latest versions. There you go. Okay. So now what I want to do is, now that we've established the goals and the software stack we use, I want to present a very brief overview of the conceptual framework that I build everything on. Okay. I'm going to present 5 questions, and those questions are going to be your new superpower. Once you answer those 5 questions, you will have clearly, I think, describe what your quantity of interest is. So you have a model, you answer those 5 questions, and then you can report the quantity of interest in your paper or in your report. That's going to be an effect of some kind, maybe, or an estimated effect. Can be an average treatment effect, can be an average treatment effect for a certain subgroup. It can be a prediction for some population. It can be a fitted value. But by using these 5 questions, we're going to describe this quantity quite specifically and clearly. So the 5 questions are: what is your quantity of interest? What grid are you evaluating the quantity of interest on? Basically, the grid is what kind of individual do you care about, right? Do you want to make predictions for someone with a high school degree, or do you want to make a prediction or estimate an effect size for someone with a university degree? Then aggregation. Oftentimes, we're going to take averages of treatment effects, right? The average treatment effect. So we're going to aggregate individual level estimates into a population or a sample level estimate. Then uncertainty. So that's what kind of standard errors are you using? What kind of confidence intervals do you care about? And then finally, test. And the test is going to be, do you want to compare 2 groups, or do you want to compare a function of groups to another? I'm going to give you now a quick definitions of all these, and what's important is that there's I'm going to talk about this for 15 minutes now, but after that we're going to review all the 5 questions in every block of the session. So when I'm going to present predictions, we're going to go over the 5 questions. When I present comparisons, we're going to go over the 5 questions. Same thing with slopes. So this conceptual framework is built into every section of the class later. All right, so what is our quantity of interest? Well, I really like this quote from Philip David, who's an eminent professor of statistics in the UK, who says that a parameter, or maybe a coefficient from your models, a parameter is just a resting stone on the road to prediction, right? We don't necessarily care about the parameters per se. We care about what we do with those parameters. And as we'll see later, a prediction is a function of those parameters, right? So we're going to use parameters to build predictions, and then we're going to use our predictions to do other things. So I want to note here that when I say prediction, I don't mean a prediction about the future necessarily. It can be a counterfactual prediction. It can be, what does my model say ought to be the average for this individual, right? Or for an individual with some characteristics. So it's not a prediction about the future. It is basically, what does my model expect the outcome to be for this person? That's what I call a prediction. A lot of people call this fitted values. That's a synonym in this case. Okay. So what is the quantity of interest is going to be our first question. Do we want to estimate a prediction or maybe a function of predictions? So what's going to be really interesting for us is that we take our predictions and then we can combine those predictions or compare these predictions to generate many of the quantities that we care about in science. So predictions, but also a contrast. A contrast is a difference between two predictions. So if I'm in a study, a medical study about cholesterol, for example, and I have a treatment group where they take the pill and have a placebo group, I'm going to estimate a model to compare these two. And then I'm going to make predictions of those two groups. What is the predicted cholesterol level for people in the treatment group? Does my model expect them to have high cholesterol or low cholesterol? And I'm going to make the same prediction in the control group, and then I'm going to compare the two, right? That's the contrast. That's a comparison. We're comparing two predictions for two different groups. So a contrast can be just a risk difference. It's a contrast. It's a difference between risks, and the risks are predictions. And it can be a risk ratio. So what is the risk of death in the treatment group, and what is the risk of death in the control group, and what's the ratio between those two risks? That's a quantity that's often computed. Then odds. I've said earlier that no one understands odds. I believe that, so don't do that, but you can do it if you want. And then slopes. So all of those quantities of interest in science can be expressed as functions of predictions, and that's what we're going to do. The second question of my 5 questions is, what is the grid? And what I mean here is, what regressor values or predictor values are we interested in? Do we want to produce estimates for the individuals in our data set, or for some hypothetical representative units? So we can do many things here. We can look at the people in my data set. So for example, in the HIV trial, what I can do is make predictions or estimate treatment effects for a very specific individual that I actually observed. So say in my data set, there's a 25-year-old man who lives far from the center. Do I want an estimate for that person, or do I want an estimate from some other person, like someone who's average on all characteristics? So I could make predictions for while holding all the control variables constant at their means or at their modes or something like that. So if this feels a bit abstract to you, the idea that we can make predictions or treatment effect estimation on synthetic units, on people with values that we have plugged in or that we've decided, don't worry, this is going to be much more concrete later. We're going to come back to this in the. But the point is, what predictor values do we care about? Our estimates are going to be different based on the predictor values that we care about. Now, aggregation is the third question we need to answer. And the question is, do we report estimates for every single observation in the grid or in my data set? Or do I report just a global summary? So when you estimate an average treatment effect, for example, you're not reporting treatment effect estimates for every single person in your data set, right? You're taking the average. It's the average treatment effect. So this is the aggregation. So we're going to be able to do an average fitted value, for example, or an average risk difference. Or we could also do aggregations by subgroup. So I could do the average predicted salary for high school dropouts, for example, right? That would be estimates at the individual level for all these people who've dropped out of high school. But then I take the average of those estimates. That's an aggregation choice. Question number 4, uncertainty. How do we quantify the uncertainty about our estimates? The main method that we're going to use is called the delta method. That's standard. Almost every statistical software out there does this by default. And the delta method is going to allow us to compute standard errors and confidence intervals for all the quantities that we present in this class, using either classical standard errors that make some sometimes unreasonable assumptions, but also we're going to easily be able to switch to robust standard errors that are consistent to things like heteroscedasticity. And we're going to be able to do cluster standard errors. There's other possibilities like bootstrap or simulation-based inference, and I'll come back to that. But of course, the simple point here is that when we provide estimates to our readers or to our colleagues, we need to quantify uncertainty. It's not okay to just give a prediction or give a treatment effect estimate. We need to be able to quantify this uncertainty to say how far off we can be. Finally, the question about test. So we're going to run a bunch of hypothesis tests in this class, or equivalence tests. And the kinds of questions we're going to be able to answer with this is, are two coefficients equal? Or is the predicted outcome of a 55-year-old engineer twice that of a 30-year-old accountant? Right? So we're going to be able to compare effect estimates or predictions, predicted outcomes, for different groups or different types of individuals or different organizations with different characteristics. Right? And we're going to be able to answer questions such as, is the treatment effect substantively equivalent to 0? Is it negligible, this treatment effect? So there's going to be so much flexibility here. You're going to be able to run all the tests you want.